As engineers and as engineering students, we know that all real devices have losses that rob them of useful output. For example, here in the internal combustion engine, there are losses in the belts, the bearings, the drivetrain, and additionally there are heat losses through the radiator and through the exhaust system. If we could define an ideal engine, one which had none of these losses, we could use it as a standard of comparison for the real device. And then we could use that as a way of defining efficiency for these devices in our thermodynamics classes. In our study of thermodynamics, we've used the concept of equilibrium to define the properties of a system, and through the properties, the state of a system. And when we've talked about processes, we've limited ourselves to so-called quasi-equilibrium processes. Those are the ones that travel through a series of defined states. For example, on this PVT diagram for water, an isothermal process might start over here at the saturated liquid region, move across the saturation dome to the saturated vapor point, and on out again at constant temperature for an isothermal process into the superheat region. All processes are not quasi-equilibrium processes. And for example, let's take this balloon. The air in the balloon is at some initial pressure, and now it's at some final pressure. I don't know how to describe the process that went on between the initial and the final state. If I had a PVT diagram for air, for example, I could define the initial and final states. Something happened in between, but I don't know how to describe it. Those kind of processes don't help us. It's difficult to describe the work done or the heat transfer for that kind of process. So we're going to limit ourselves to discussing quasi-equilibrium processes. Even for those kinds of processes, there are differences between idealized processes and real processes. One of those differences is caused by the presence of friction. Let's look at an ideal piston cylinder system that is perfectly insulated. The piston here is of negligible mass, so we can ignore inertial effects. The piston compresses the gas in the cylinder. The PV diagram for the gas shows an adiabatic compression from state 1 to state 2. For the ideal case with no friction, the gas must always exert a force on the piston face that balances the force exerted by the connecting rod, so the piston is in mechanical equilibrium. To move the piston downward, the gas must also exert a force that balances that of the connecting rod. For this idealized case, the PV path for compression and expansion are overlaid. This quasi-equilibrium process is reversible, because if the piston is stopped and moved in the opposite direction, the PV curve will be retraced back to the starting point. Now let's include friction between the piston rings and the cylinder wall. The connecting rod must now exert a larger force on the piston. This new force must both compress the gas and overcome the friction. The connecting rod is now forced to do extra work to overcome the friction. However, the PV diagram for the gas is the same as when friction is absent, because the gas itself is exposed to the same process as for the frictionless system. Now, consider the expansion process. The friction force now acts in the opposite direction. The gas must do work on the piston and must provide not only the force necessary to balance the force exerted by the connecting rod for the frictionless case, but must also now overcome friction. The gas pressure is therefore greater throughout the expansion process than it was during the compression process. The PV diagram for one compression and one expansion then looks like this. The gas pressure must somehow be increased from P2 to P2A before piston movement can begin. Perhaps this can be done by constant volume heat transfer. The gas pressure in the cylinder can then provide the additional force necessary to overcome the friction during the expansion stroke. The pressure in the gas at the end of the expansion stroke, P1A, is not equal to the pressure at the beginning of the compression stroke, P1. To get back to state 1 from 1A, we have to do something else to the system, such as cooling the control mass at constant volume. The cycle of compression, heating, expansion, and cooling processes can be repeated. The work necessary for the gas to overcome friction on the downstroke is the area between the upstroke and downstroke curves. The compression-expansion process in the presence of friction is irreversible. It's impossible to stop the piston at any point and retrace the PV path to the starting point. All mechanical processes in the real world involve friction. These include friction in sliding contacts such as in journal bearings, rolling friction of tires, roller bearings, and wheels, fluids flowing over surfaces, and fluid interactions that cause the formation of eddies. So we might expect that every real process that involves motion will be irreversible. It appears that in real processes, motion always involves friction, and friction always causes irreversibility. Suppose we consider some real processes that do not involve motion. Are they reversible? The first law classifies all energy transfer into the categories of work, heat transfer, and mass transfer that carries energy across a boundary. Work and mass transfer across a system boundary always involve motion and friction, and therefore always are inherently irreversible. That leaves only heat transfer for us to consider. So let's examine the heat transfer process. Heat transfer does not necessarily involve macroscopic motion, only the presence of a temperature difference. Let's examine heat transfer processes to see if they are reversible. Consider again the piston cylinder system. Consider first a frictionless piston cylinder system, but remove the insulation so heat transfer can now occur between the gas in the cylinder and the surroundings, which are at temperature T sub E. Suppose the initial gas temperature T sub 1 is considerably larger than T sub E. During the compression process, the gas temperature tends to increase because work is being done on the gas. Heat transfer occurs from the gas because of the temperature difference between the gas and the surroundings. A TV diagram in that case looks like this. The gas temperature is less at all volumes than for the adiabatic case because of the heat transfer. Now consider the expansion process starting at point 2B. The control mass remains at a greater temperature than T sub E, so heat transfer during the expansion is still from the gas to the surroundings. As long as the gas temperature does not fall below T sub E during the expansion, the gas will continue to lose energy by heat transfer to the surroundings. Thus, when heat transfer with a reservoir at a different temperature is present in this system, the process is irreversible. We again must do something else, such as heating the gas at constant volume, to get back to state 1 from state 1C and complete the cycle. Do we conclude that all heat transfer processes are then irreversible? No. Consider the same process, but let's carry it out very slowly. The temperature of the control mass comes to thermal equilibrium with the surroundings at each intermediate state, and the gas temperature will always be very close to T sub E. The process for the control mass then becomes a constant temperature process throughout both the compression and the expansion. Even though heat transfer is occurring, this process is reversible. So heat transfer processes are in general irreversible when the heat transfer occurs because of a finite temperature difference between the system and the surroundings. But a heat transfer process can be nearly reversible when the heat transfer is driven by an infinitesimal temperature difference between the control mass or control volume and its surroundings. For any real process involving heat transfer, the temperature difference between the system and its surroundings is always made finite, so all real heat transfer processes are irreversible. There's one other process we haven't considered, and that's the mixing of two or more components. Is that process reversible or irreversible? Well, we can check it out. Here's a box that contains separated balls of red and white, and we can mix them just by mixing. And now we can check to see whether the process can be reversed. And I'm going to mix them again. As you can see, they're back in their original configuration. Red balls on one side and white on the other. You don't believe that? A little bit of video magic that we did? Well, you're right. The mixing process is irreversible, and the balls will not unmix if we keep shaking the box. Whenever we mix two or more components, the process is irreversible. And here are some other examples. We have found that all real processes that involve work, heat transfer, or mixing are irreversible. We can imagine ideal devices where no irreversible effects are present. Such devices must be frictionless, be either adiabatic or have heat transfer that occurs over infinitesimally small delta T's, and must involve no mixing. No practical engineering systems meet these constraints. It's hard to tell how far any real device will deviate from ideal behavior. But what we can do is predict ideal behavior by assuming that all processes are reversible. And if we do that, we can predict the maximum possible output, for example, from an engine like this one. And that's one of our goals in thermodynamics.